Welcome everybody. I am Ahmed Al-Agami Musa. I am a senior cardiology resident at Vena Cardiac Center, Cottbus in Germany. Today I am going to talk about the estimation of pulmonary artery systolic pressure with echocardiography. In order to know the idea upon which the estimation of pulmonary artery systolic pressure is based, we have to know the normal intracardiac pressures. Let's take a look at this slide. This slide shows the normal intracardiac pressures. The normal pressure in the right atrium is about 0 to 4 or 5 millimeter mercury. The normal right ventricular systolic pressure is about 25 millimeter mercury, and the normal pulmonary artery systolic pressure is also about 25 millimeter mercury. Then the right ventricular systolic pressure equals the pulmonary artery systolic pressure, provided that the patient has no pulmonary valve stenosis. We can take a look on the left side. Also, the left ventricular systolic pressure equals the aortic systolic pressure, about 120 millimeter mercury. Unfortunately, we can't detect, or we don't have a method to directly estimate the pulmonary artery systolic pressure. But when we have a method to estimate the right ventricular systolic pressure, then we can know the pulmonary artery systolic pressure. The method that we currently use to estimate the right ventricular systolic pressure was developed about 300 years ago by the Swiss mathematician Daniel Bernoulli. Here is Daniel Bernoulli. Daniel Bernoulli has developed an equation called Bernoulli equation or the Bernoulli principle, and we have done a modification for this Bernoulli equation called modified Bernoulli equation to estimate the right ventricular systolic pressure. The modified Bernoulli equation states that P1 minus P2 equals 4 times the velocity squared. What does this mean? I will explain that, but with a simple math trick, we can transfer the P2 to the opposite side of the equation. Then P1 equals 4 times the velocity squared plus P2. What is P1? What is V? What is P2? P1 is the pressure in the right ventricle, is the right ventricular systolic pressure. P2 is the right atrial pressure. And V is the maximal velocity of the tricuspid regurgitation jet between the right ventricle and the right atrium. In this equation, we have 3 unknown factors. P1, the right ventricular systolic pressure, which we need to know, and V is the maximum velocity of the tricuspid regurgitation across the tricuspid valve, and P2 is the right atrial pressure. When we find a way to know the right atrial pressure, and when we know the maximal velocity of the tricuspid regurgitation jet, then we can estimate the right ventricular systolic pressure, which equals to the pulmonary artery systolic pressure. Then we have to know the maximal velocity of the tricuspid regurgitation jet and the right atrial pressure in order to get the right ventricular systolic pressure or the pulmonary artery systolic pressure. At first, how we can get the maximal velocity of the tricuspid regurgitation jet. We need to get a tricuspid regurgitation signal. Here I have done an apical 4-chamber view. I have placed the color Doppler over the tricuspid valve, then the continuous wave Doppler. Then we get a signal like that. Here is a tricuspid regurgitation signal. When we measure the peak velocity of the tricuspid regurgitation signal, then we have the V. But how we can get the right atrial pressure? We can estimate the right atrial pressure from the vena cava inferior, from the inferior vena cava. Here is a subcostal view, shows the inferior vena cava. When we measure the diameter of the inferior vena cava, and when we see whether the inferior vena cava collapse with inspiration, we can estimate approximately how high is the right atrial pressure. I will explain this in further details in the next slides. Then, in order to estimate the right ventricular systolic pressure, we need continuous wave Doppler over the tricuspid valve or over the tricuspid regurgitation jet in order to measure the tricuspid regurgitation jet Vmax or maximal velocity. We need to see the inferior vena cava to measure its diameter and to see whether it collapses with inspiration and the degree of collapse in order to estimate the right atrial pressure. When we have right atrial pressure and maximal velocity of tricuspid regurgitation, we can get the right ventricular systolic pressure. At first, how we measure the tricuspid regurgitation maximal velocity? As I have said, I get at first a 4-chambered apical 4-chamber view. I place the color Doppler over the tricuspid valve. Here the patient has moderate tricuspid regurgitation. I place the CV Doppler in the middle of the tricuspid regurgitation jet. Then I get a tricuspid regurgitation signal like that. Here we can measure the peak of this signal. Here we have a tricuspid regurgitation Vmax around 3.8 meter per second. As we have already seen, in order to measure the right ventricular systolic pressure, we multiply the peak or the maximal tricuspid regurgitation velocity. We have to square the number that we get, 3.8 squared, then we multiply it by 4 to get this amount. Then we have to add to it the right atrial pressure. You can calculate it one more time. The machine have already made the calculation. 3.8 square, 3.8 multiplied by 3.8, then multiplied by 4, we will get 59 millimeter mercury. An important thing to know when we measure the maximal velocity of the tricuspid regurgitation is to know where to measure. Here we have the signal of tricuspid regurgitation the same slide, the same patient, and the signal. Which peak should we measure? Here we see that tricuspid regurgitation envelope has two parts, a dense one, and here we see a less dense or slightly bright part. What is right? To measure the dense envelope or to measure until here? The correct one is to measure only the dense envelope. I have zoomed in to show it one more time. Here I have measured only the dense envelope. Here I have measured also the bright part. However, the correct method is to measure only the dense envelope. Here we have a maximal pressure gradient about 59 millimeter mercury. But if we do it in the wrong way, we get a pressure gradient of 77. Look at the difference. As we have already said, we make square or we multiply this number by itself, then we multiply it by 4. That means when we make a small error, we would multiply this error, and at the end we will get a big difference, about 20 millimeter mercury, if we do it in the wrong way. Measuring the dense envelope, not the bright one, is a rule called chin, not the beard. Chin, here is the chin of the face, here is the beard. We measure only the chin, not the beard. Never forget, chin, not the beard. Here is the chin, here is the beard, here is correct, here is wrong. In order to use the modified Bernoulli equation, we need a tricuspid regurgitation jet. But what if we have no tricuspid regurgitation? When we don't have a tricuspid regurgitation jet, we don't worry, or we don't have to measure the pulmonary artery systolic pressure. As long as the patient has no tricuspid regurgitation, that means that his pulmonary artery pressure is most probably normal. Sometimes we have patients that have mild tricuspid regurgitation, and the tricuspid regurgitation signal is relatively weak. We don't have a dense signal. We don't know whether the peak is here or a little bit lower. We don't know how to measure this. We have two options. As theoretical option, we can inject the patient with agitated saline, and the agitated saline will make the tricuspid regurgitation signal more prominent, but we rarely do this in clinical practice. The second method I would prefer to do is to ask the patient to take a shallow breath. When the patient takes a shallow breath, with inspiration, the venous return to the right side of the heart increases, which makes the tricuspid regurgitation jet more prominent, and we have a more prominent tricuspid regurgitation signal, which we can easily measure, like here. Here's the patient before inspiration. Here's the patient have taken a shallow breath, and the signal is much more better. A third one more limitation, if the patient has a very severe tricuspid regurgitation due to coaptation defect. Here, like this patient has a massive tricuspid regurgitation. Here we can see a coaptation defect. The tricuspid valve does not close. Here, when we measure the pulmonary artery systolic pressure, or when we want to estimate it, it would be most probably underestimated because we almost have no pressure gradient between the right atrium and the right ventricle. They are almost one chamber. That means when the patient has a very severe tricuspid regurgitation with coaptation defect, we can't estimate the pulmonary artery systolic pressure accurately. I have showed how to measure the tricuspid regurgitation Vmax, then how we can get the second part of the equation, how we can estimate the right atrial pressure. At first, we have to get a subcostal view of the inferior vena cava. We have to measure the diameter of the inferior vena cava. And the second part, we have to look for the inspiratory collapse of the inferior vena cava. When the patient takes a breath, when the patient inspires, the intrathoracic pressure increases, which pushes the diaphragm. That also increases the intra-abdominal pressure, and the intra-abdominal pressure will increase, and the increase in the intra-abdominal pressure would compress the inferior vena cava normally. But if the pressure in the inferior vena cava is high, it will not be compressed during inspiration, or it will not be completely collapsed during inspiration. Then we have to measure at first the diameter of the inferior vena cava and look for inspiratory collapse. We can measure the diameter of the inferior vena cava either from the 2D image, from here, or I like to do it with M mode. I place the M mode over the inferior vena cava about 2 centimeters from its drainage in the right atrium. Then we can get a picture like that. Here is the inferior vena cava in expiration. Here I have measured its diameter. It's about 1.9 centimeter, and here is the inferior vena cava in inspiration. It collapses. It has collapsed, and the diameter is about 0.7 centimeter. It has collapsed by more than 50%. This slide summarizes how we can estimate the right atrial pressure from inferior vena cava. At first, we have to measure the diameter. Normally, the inferior vena cava has a diameter below 20 millimeter. If the diameter of the inferior vena cava below 20 millimeter and its inspiratory collapse more than 50%, then the right atrial pressure, or we can call it the central venous pressure, is normal, about 0 to 5 millimeter mercury. But when the inferior vena cava has a diameter more than 20, we have to look for the inspiratory collapse. When it has a normal inspiratory collapse more than 50%, then the central venous pressure is about 5 to 10. When the inspiratory collapse is below 50%, then the right atrial pressure about 10 to 15 millimeter mercury. When we don't have inspiratory collapse at all, then most probably we have a right atrial pressure more than 20 millimeter mercury. Let's see some examples here. In this case, here we have the inferior vena cava. We have placed the M mode. Here, the inferior vena cava collapses with inspiration, but we have to measure it. Here in expiration is 1.9, in inspiration 0.7. That means inferior vena cava diameter is normal, below 20, and inspiratory collapse more than 50%, that means that the right atrial pressure is normal, about 0 to 5 millimeter mercury. The second case, here we have an inferior vena cava which collapse. We have measured it. Here in expiration, it is about 1.9 centimeter. In inspiration, 0.5. Then we have a diameter below 20 and collapse more than 50%. Then we have one more time normal right atrial pressure there about 0 to 5 millimeter mercury. Another case, here we have a dilated inferior vena cava in 2D image. We have placed the M mode. We have a picture like that. Here we have measured the vena cava inferior in expiration is about 3.1 centimeter. So it is dilated, markedly dilated, and with inspiration it is about 2.6 centimeter. Then we have dilated vena cava inferior more than 20 millimeter, and inspiratory collapse below. Inspiratory collapse is below 50%. Then, according to our slide, the right atrial pressure in this case is about 10 to 15 millimeter mercury. Our next patient, he has a markedly dilated inferior vena cava. We have placed M mode. Here we have expiratory diameter 2.2 and inspiratory diameter 2.2. So the inferior vena cava does not completely change with inspiration. More than 20 millimeter, no inspiratory collapse. Then according to our slide, we have a right atrial pressure more than 20 millimeter mercury. Then from the tricuspid regurgitation Vmax, we can estimate the pressure gradient. The pressure gradient we get when added to the right atrial pressure estimated from the inferior vena cava diameter and its inspiratory collapsibility, we get the right ventricular systolic pressure, which equals to the pulmonary artery systolic pressure. Here is the grading of pulmonary hypertension. When we get a number from our modified Bernoulli equation, we have to look at it. When the number we get is below 25 millimeter mercury, the patient has no pulmonary hypertension. He has normal pulmonary artery systolic pressure. From 25 to 40 is borderline. 40 to 50 millimeter mercury, we are talking about systolic pulmonary arterial pressure. The pressure we estimate in echo is the systolic pressure, not the mean pressure. When we have a value between 40 and 50, that means mild pulmonary hypertension, 50 to 60 moderate, and more than 60 millimeter mercury is severe pulmonary hypertension.